So should I start?
Yes, we have. I think the recording has been started. Yes, you can.
Yes, yeah. Right. So today I'll be presenting most of my my PhD thesis, the focus of my PhD thesis, which is basically understanding the relationship between scene level sketch, text, and images or photos. And before I dive deep into it, I'd rather motivate this topic by saying why is sketching important. And the argument here is that sketching is a universal language that anybody can speak, understand, regardless of their technical background. And to support this argument, there has been several researches where even infants or various tribals, which those who have never seen sketches before, even those people can understand sketches when they are shown to them. And not just the infants and tribals, which are humans, but even chimpanzees, they can understand sketches. So it basically says that, okay, people are developed biologically to understand photos, but they are also developed biologically to understand sketches. And hence, it forms a very important modality of this visual cognition process. And it deserves its own discipline. And this visual sketches, and the important part here is that sketches are perceived as easily as photos, as shown by these two research papers. And while this scene or photos has got really good attention with this Oscar, Burt, and Clip, very recent and famous papers, sketch modality, like, it needs more progress. There isn't sufficient momentum in the sketch modality, in spite of it being an important part of this visual cognition process. But of course, there has been some very crucial and important work, starting it can be traced like long back till BMVC 2013, where people would do mostly handcrafted thing. And then this BMVC 2015, the best sketch, it's sketch recognition still. And it's the first time we see that a machine can understand object level sketches better than a human can. And some follow-up works, of course, is that then the power of sketches as a fine-grained retrieval for fine-grained image retrieval was explored in Sketch Me That Shoe in CVPR 2016 oral paper. And of course, the collaboration between SketchX and CVC Lab was doodled to search the zero-shot sketch-based image retrieval, CVPR 2019 oral. Finally, I'll talk about these two papers. One is that the application of RL for retrieving sketches. It's the main core principle of the CVPR 2020 paper is that you don't need to draw the chair completely or the stool completely. You can draw part of it and you can still do a good enough retrieval process. So that tells you that, okay, even for object sketches, forget about recognizing the objects. Even part of the drawing helps you to recognize that particular object. And finally, this Pixelar SIGGRAPH Asia 2020 paper, where it's been shown that the game of Pixelar is basically where an AI or a machine tries to draw an object, say a cat, and it wants it to draw it in such a way that it's recognizable with the least amount of strokes. So as you can see, the whiskers and the ears, the pointy ears, they help in a better recognizability. But the underlying principle of the SIGGRAPH 2020 paper is that a machine can draw a sketch more recognizable or quickly recognizable sketches, and that's very fascinating. And this shows that the significance of the amount of work that has gone into understanding object level sketches. But the problem is you can only express so much by drawing objects, and there is this huge modality that's remaining out there, which is scene sketches. And our topic on my research is mostly focused on getting and decoding this mystic information in this object scene level sketches. Now there has been some significant attempts at scenes understanding scene sketches, but one of the basic challenges before even you attempt understanding scene level sketches with data driven machine learning techniques or something is you need to get a data set first. And and there was the need of this data set and understanding scene level sketches was recognized or realized by researchers as early as 2018 in ECCV, where the first data set was proposed, sketchy scene. As you can see, they were like cartoon-like images for which you would get the sketches, and it would help you in doing fine-grained retrieval or this kind of various image colorization or sorry, sketch colorization and all these different tasks, which it could potentially uh, s- uh, happen. But the problem with these this particular data set, or this at first attempt on understanding scene level sketches, is that these sketches are not really drawn by humans. As you can see, they would have this object level and they would do a drag and drop and arrange those object sketches in a scene. But that's not really a human drawing. As you can see, these kind of house or the girl that you in the slide, a human is unlikely to be able to draw such perfect houses, or perfect dog or like that. And the motivation for using this kind of annotation is that like collecting human drawn scene sketches is very taxing, and it's not like they couldn't scale it up. Second approach, the second attempt was in CVPR 2020, where how they would do is that they would collect a data set like this, but they are computer generated or like synthesized. They would use this COCO data set or COCO photos, and they would use the semantic segmentation to synthetically create the elephant in that particular. They will copy and paste the elephant objects in that regions. But again, the problem here, you're still stuck with that it's still computer generated. The first one was not human drawn, the second one was completely computer generated. And if you want to understand scene sketches, and mostly a scene sketch is a modality of expression of humans, and you need human like sketches. So of course, so what can we do? We need to collect human-like sketches, but this collecting scene sketches is very taxing process. And this is exactly where our first solution comes in, is this: get a proper data set where the sketches are actually drawn by a human, so that so that data set would lead to the studies of how humans draw, or the drawing strategies and other intuitions that it can bring. So we've proposed this kind of data set, which is FS COCO. We call it FS COCO, which is FS stands for freehand sketch, and COCO comes from this because the images or the photos that we take is from COCO dataset, MS COCO dataset. Our dataset, the few of the samples, that this is how our dataset looks. As you can see, that they are not overly artistic, overly detailed sketches or something like that. These are sketches we want, like what an average person thinks or what an average person can draw about a photo. And that's what we want. We want recognizable, because we as a human can recognize each of these sketches. They're not really good, like really beautifully drawn, but we can recognize them. And that's exactly our point here, that an artistic sketch doesn't scales to everyone and it takes more time. Let's go with something which is drawn by an average human and does not take that much time. To give a more brief of what this dataset contains, this dataset is taken from, like as I said, from the MS COCO photos. So we have the photo and its caption, the photo caption, such as the white sheep standing on a dry grass field. And then from the photo, we ask a human to draw a sketch of and the sketch is drawn. From that sketch, we again collect what we call a sketch caption. Now, if you compare the photo caption compared to the sketch captions, i.e., the textual description of sketches, you would notice that first, these sketch captions focus more on the salient regions, like the sheep or the horse is standing near a fence, things like that, or next to a tree, things like that, rather than a brown. The color information is definitely not there, but dry grass, these kind of adjectives, these are also pretty much missing. So in some ways, it helps you focus on the salient regions or what the human thinks is important here, but you do miss some information such as color. And the benefit of collecting sketch captions versus image captions, it helps you compare these two what sketch modality can express and what photo modality can express. The problem with photo modality is that there is too much information. Like you don't know where to focus, which is why there is a separate field in computer vision, which is like understanding the human saliency. Sketch gets you the human saliency off right off the box. Before we go dive deep, we'll talk a bit about the data set, some statistics. Note here the sketchy scene and sketchy coco, they are both. Sketchy scene is like those not human drawn, and still, and ours FS coco is human drawn. We collect 10,000 sketches, whereas the existing they are 14,000 or 7,000, and in spite of being machine generated. So which says that our data set in scale wise is significantly matching the existing ones. And not just that, our dataset has 92 categories. Categories could be a horse, could be a zebra, like that. It has 92 categories compared to the existing, such as 45 or a mere 17 categories. So it's pretty diverse. So if a model performs good on these FS Coco images or for sketches, it means that it can actually understand a diverse sketch setup. And that's really what we are looking for from this particular dataset. Now, I'll just briefly describe how we do collect the data set. Our objective, as we've mentioned, that we want to collect recognizable but not too detailed or too artistic sketches, something which is why we call it freehand or drawn by naive users. And this drawing process, the process is very similar to the one of the benchmark TU Berlin, all these kind of sketch collection data set, where you basically we show the photo for 60 seconds and then we ask the user to draw the sketch from their memory, i.e. the photo is then removed after 60 seconds. We did conduct a pilot study with 10 users and to find out, okay, what is the optimal viewing time and what is the optimal time required to draw the sketch. And we find that, okay, 60 seconds you should be allotted to view the sketch and 180 seconds or 3 minutes should be allotted to draw the sketch. And as you can see, this 3 minutes is not a lot of time. So you would have only, you're kind of implicitly forced to draw the salient regions. And the photos, of course, are taken from MS Coco. And the reason being it's pretty diverse. It has a lot of categories sufficient. And the other interesting fact is that we did collect 10,000 data sketches, right? And these 10,000 are collected by 100 annotators. Each annotator is drawing 100 sketches. Of course, we do get one sketch for each photo. That's true. But these 100 annotators, you can do like various, this can lead to other studies like how is different people drawing, or are they drawing the same thing or not? Now, brief of what is, I'll not go into detail of all this because it's like, it would be good if you read the paper about it. But what this dataset can possibly lead. First of all, it's the first freehand sketch dataset. It can help you lead to fine-grained sketch-based image retrieval. But here's the human-drawn freehand setup. You can compare SBIR, sketch-based image retrieval, text-based image retrieval, or sketch plus text-based image retrieval by, and then you can do this kind of meta adaptation, i.e. do all people draw the same? Like, for example, if a model works good enough for me, would it performance harm when it generalizes to your drawn sketches? And of course, a hierarchical, these scene sketches are much more complex than object level sketches, and you would need these kind of newer algorithms, as we proposed a hierarchical decoder to handle this complexity of scene level information. There would be like more than 2000 points, and a simple RNN based approach would not suffice to model 2000 points, where an RNN can usually model 200 to 300 points. So that motivates this kind of new algorithms which could be developed to handle the scene complexity. Now, few of the insight, now apart from the technical details, few of the insight, what does FS Coco tell us about this drawing strategy? So these two graphs, the first is a normalized time, the stroke length, as you can see, as the user keeps on drawing towards the end of it, the stroke length keeps getting smaller and smaller and smaller. So initially the human starts with drawing longer strokes. Towards the end of the sketch, they draw smaller strokes. And this graph tells us, okay, people draw a more coarse to fine-grained approach, i.e. they would draw. And the second approach is that we see, what we do is that given the vector, because we have the vector information of a sketch, what we can do is that we mask some of the strokes that a user had drawn initially versus some of the strokes that the user had drawn towards the end of their sketch. So the red line here denotes the one which is when we are masking or we are removing the strokes drawn in the beginning, and the blue line shows the one that we removed when the strokes towards the end. If you remove the strokes that are drawn towards the beginning, it hurts retrieval, image retrieval performance, which says that the sketching strategy followed by all these 100 users, they align towards this. Humans, they draw a more, like they draw longer and more salient strokes early on. And that's although this observation has been seen for object level, we show it for the first time in such a large setup for scene level sketches also. And that tells how a human draws. And this is very insightful, an observation that we observe from the data set. Now, the second part is that, like, we'll come back to this photo, that even from the photo, like research has shown that humans can perceive a sketch as good or as easily as a sketch. But can machines perceive a sketch as easily as photos? And that's exactly what we are trying to answer with sketch captioning. Because we use captioning because image captioning has been used as a benchmark setup for understanding scenes. And we want to show that is it the same thing is transferable to machines. The perception can be transferred to machines. And the answer is yes, machines can perceive sketches, as you can see with the image captioning results and sketch captioning results. But yeah, with sketches, the performance degrades. So it's like, yeah, machines find it more difficult to understand sketches compared to photos. Now, but on the other hand, it has research has shown that humans can do them equally good. And so there is this kind of gap in this machines of how machines perceive sketches. And probably this gap with that should be bridged, and the sketch captioning results probably in the future should improve and match to its image captioning counterpart, or at least be close to it. Now, apart from this data set, I'll go on to the next topic. Like we'll first explore this fine-grained sketch-based image retrieval, but for scene levels. And the question here is that we already had object-level fine-grained sketch-based image retrieval. A lot of papers that we have discussed. One of this early work is here in CVPR 2016 oral. Now, is the same algorithm transferable for scene level FGSBIR? Now, that's the biggest question here. And the answer I would say is, well, scene level has some additional challenges, which is that it has this thing called partial. You see, we have overlapped a sketch drawn with on top of the photo, and in the photo there are like 9 sheeps, but in the sketch there are hardly 4. Or even the bicycle that's been drawn, the bicycle, the size is smaller than its photo. Now, or the alignment, so i.e. sketches might not describe everything that is in the photo, or even if you're describing, it might not be perfectly aligned, and we call this problem as partialness. And the thing with partialness is that like we need, like, as the sketches become more and more partial, the performance drops. Now this partialness is not so much pronounced in object level, which is why we come up with the CVPR 2022 paper that partial does it, where we explored, like, okay, why, what is wrong with these object level, the algorithms used for object level FGSPIR, and what should be improved. And the culprit, what we call, is this global average pooling. Like you take the sketch and the photo and you combine them to global feature vector, and you just match the L2 distance or cosine distance. The problem is that some regions empty, there are empty white regions in the sketch, and there is whereas the photo is a very dense representation. So what you should ideally do is probably you can break the photo or the sketch into patches and then match the patches among each other in a weighted fashion. And that's exactly our solution. We come up with 2 additional losses, or this a new distance metric, which is more partially aware and more suitable to the scene level FGSPIR. And I'll briefly glance over the technical details of how we say, and an important thing is that we do not radically change the baseline. Rather, we just reinterpret the existing solutions for object level fine-grained sketch-based image retrieval and just tweak it a little bit by adding a weighted vector to the existing formulation. And if we play around with the formulation, we see that it looks a lot like an optimal transport problem. The weighted FGSBR equation looks like an optimal transport problem. If you have an optimal transport problem, you can convert to a parametric form. And then from the parametric form, you have this combined or unified equation, which we call the Lagrangian, which combines the equality and inequality constraints for an optimal transport problem. Finally, if you have the Lagrangian, you use the Slater's condition and the KKT conditions, and following Dini classical, and you can get the gradients. I.e., if you get the gradients, you can backprop, and you can learn in this kind of weighted FGSBIR, and which would help you to get this distance metric, which is partially aware. Now, does it really help? And of course, we do the quantitative studies where we see that yes, the first is the complete sketch. Now, the complete sketch is basically you do not disturb the entire sketch, you use it for retrieval. And then we have a P mask of 0.3, i.e. you would randomly mask 30% of the strokes in your sketch, and you would see how good the retrieval performance is. And overall, and then you mask 50% of the sketch, and you see the proposed method with this new distance metric is much more stable compared to the existing. The SOTA, as you can see, these are basically some of the approaches being used, or the algorithms used for object level FGSPIR, and they have been naively extended to scene level, and that really doesn't work. The results drop sharply as the sketches become more and more partial, or more and more empty regions pop up in the sketch. Now that's a very technical detail. What does it, as an intuition level, how does this approach help? So I'll say one of the side benefits of this thing is that you get this interpretability of how scene level FGSBI works. Now this visualization of the heat map is that we said, okay, we want to convert a naive baseline sketch-based image retrieval into a weighted sketch-based image retrieval, and these weighting are gone for each local photo and sketch regions. Now, if you visualize these weights, you get this kind of heat map in a sketch as well as a photo, and you can see, okay, which regions in a sketch is being highlighted compared to a photo. Take the example on the right hand side, which is sketchy scene here. This flowering pot or the watering pot and the fence, these are highlighted. And the same regions in the photo is also highlighted. Come to the sketchy cocoa, you see there are 2 giraffes in the photo, whereas only 1 giraffe in the sketch. Now the sketch knows exactly that, oh, okay, the giraffe is the most salient regions for recognition, and you can see the heat map is more or less uniformly spread across these two giraffes. So this tells us, okay, which region in sketch was contributed towards the retrieval process. And you don't have to additionally make formulations for it. It's just the same loss function gives you this kind of nice and cute solutions to that. Now, we have talked about this data set and how this data set helps us about the sketching strategy. Next, we talked about this kind of new scene sketch level specific problem of the partialness that they face, and like how it requires its own mathematical formulation to overcome this approach. Next, in the finally, we'll talk about this kind of the more hierarchical of unifying finally sketch, text, and photo. Because up until now, we were trying to understand how humans draw and what are the scene level sketch specific problems and what sketch captions could bring. But it's like the question that we are trying to answer here is that is sketch and text complementary? Because both sketch and text are a human way of human expression. So, and you can describe some things via text and some things via sketch. So sketch can give you more fine grained details, whereas text, they just help you describe the color information or things like that very easily. But if you can combine them, and this is, and not just combine them, you have this information from sketch and text and photo, and you would want to develop this kind of a unified common embedding space. Now apparently it turns out it's not that quite easy to do that, and we have to, because sketch, text, and photo, they are quite significantly different modalities from one another. And to do that, I wouldn't go in detail of the technical details of it, but I'll give you some of the key points. It's the one of the paper, we call it scene triology. It's there in archive. So the more all the key highlights of this approach is that you would need what we call it a modality agnostic information, i.e., the information that you can share across sketch, photo, and text, and this modality specific information. Now, what can be a modality specific information is that something which is specific to sketch, something which is specific to photos or to text. Now, one of the modality specific information for text would be your grammatical or linguistic knowledge, like this and the modality agnostic from this text domain or modality would be the semantic information that the horse is standing next to the fence. This information, the semantic knowledge, is something which is modality agnostic, which you can share across modalities. And the modality specific information is something like this grammatical, like are, the horses are standing next, like that kind of informations. So to split this information, we can come up with this kind of interpretation of information bottleneck, where we show that how this information bottleneck helps in this splitting of information into modality specific and modality agnostic, and few of the benefits of this splitting information and how can you combine sketch and text. We combine sketch and text using a technique which we call multi-head attention or set attention, because because set if you use a set interpretation, you imagine sketch, text, and photo. If they are elements of a set, then the representation of set is independent of the number of elements, i.e., you can have only sketch to photo, you can have sketch plus text to photo, or just text to photo. So this kind of, so not going details, what does this unified representation or this new approach helps us do? Now, previously we had talked about like we can do sketch based image retrieval, text based image retrieval, or sketch plus text based image retrieval. This unified, this new, this scene triology, it's just you have one framework which can solve multiple tasks. So the first task you can see, that is the sketch-based, fine-grained sketch-based image retrieval. You would give a sketch, you want to retrieve a photo. The same network, as we have seen in the previous slides, it can perform this, and it does a pretty good job. Now see, the results in the proposed approach is not super good compared to the baselines, but that's not the point here. The point is that can you match or be competitive to the baselines? And we see it's actually outperforming by a small margin at least. That's sketch-based image retrieval. The same network can also perform text-based image retrieval. That's a good, and it goes pretty competitive. Maybe sometimes it performs inferior to clip models and all, but it does a pretty good job. And then finally, you can do sketch plus text-based image retrieval with this using the same network. Now, up until this, because these are all retrieval approaches, right? Which makes sense. Fine, it's not probably not so super non-trivial. But now if you think of that same network can also perform image captioning, which itself now, given the state of the art, it's pretty challenging task. And we see that yes, the same network can perform a pretty competitive for even image captioning approaches. And not just image captioning, it can also do sketch captioning. So in essence, what we're trying to get with this unified common embedding is that we want to map any two modalities, sketch, text, and image, with one another. And maybe this common, but when you map all these modalities together, maybe when you this kind of text can improve or help in a better retrieval, or sketch can perform it, contribute its own important information like that. And that's basically the final objective of this, of my thesis up until now, that first understand scene sketches, then see is the same algorithms used for object level sketches applied to scene level sketches, and we see okay, no, there is this problem partialness. And finally, can we really combine sketch, text, and photo, and just one framework which can map any two of these two modalities in a fine-grained approach. And we see that yeah, the same framework can perform pretty competitive in all these, not just generative tasks such as image captioning, as well as retrieval tasks, sketch-based image retrieval, text-based image retrieval, or sketch plus text-based image retrieval. And yeah, that's basically the short presentation. Yeah, if you guys have any other any more questions.
Thank you, Pinaki, for the presentation. It was very insightful, and well, I will just go on to the audience and everyone here. For sure, they might have some questions.
Right.
Yeah, so Joseph will start.
Well, I don't know if a question or a comment. In the process of creation of this data set, this FS,
Coco. Yeah.
If I understood, the person, the drawer, has an image during few seconds, and then at the end the person reproduces what remains of this image. So
Yeah.
at the end is not really a conceptual drawing, but is a kind of you also mentioned that it is a kind of saliency reproduction. No, it's the person is trying to copy in a simplified way the scene.
Yes.
If the experiment was different, just showing to the user only the caption. So, for example, you have a scene where there is a cat in front of a tree. If you see the photos, you will try to reproduce the cat and the tree in the same position, exactly as it appears in the photo. If you just ask the user draw a cat in front of a tree, you will have different variations of the same objects in different positions.
Right. Right.
So then, if you go to sketch-based retrieval, it's again the same. If you have trained the system with sketches that reproduce photos, at the end you are able to search for those saliency maps that people have learned, not a conceptual search. So this is, as I said, it's not a question; it's more a comment that sketch processing for me has like two directions. One is a more conceptual task that is draw a cat and then how people is drawing a cat, or reproduce this photo and then it's more shape recognition or saliency recognition more than the conceptual way of drawing.
So I think with this, when you use text as a prompt, because if you understand your comment, is that instead of using photo as a prompt, why not use text as a prompt and then you draw the sketch? Now, with when using text as a prompt for drawing sketches, it's like the prompt is much more a weaker prompt, or it doesn't describe everything, So you can be more creative here. And if a process, when you use text as a prompt to get these sketches, you would get more creative sketches, right?
Exactly.
And yes, so the creativity is something that you cannot explore from this particular data set. But also the create, but that something we purposefully right now we didn't address it, because creative sketches, because you are giving this 3 minutes time, and within these 3 minutes, how much creative can you get? And even if you had a creative thought in your mind, can you really depict it? Now it's basically boils down to the scalability problem. Because right now we need sufficient data set to make some of how humans draw, rather than how creative humans can get with their sketches. So very similar paper for this would be Devi Parikh's paper. I think you would all know the iClear paper with a creative sketch data set, where they would basically ask. So the prompt in those data set is that, suppose you're trying to draw a bird, and but you've been given only the wing, and the algorithm or the prompt is basically a part of the sketch or the object, such as wing or a beak, is drawn, and then you fill up the rest. So what the prompt should be can change the decision of how creative your sketch can be. But here's the thing: creativity is a more difficult problem rather than understanding sketches. And definitely creativity has been explored for object level only up recently, and but creativity could be more explored for scene level approaches also. And that could be an a future direction, of course, of how creative your sketches are.
Just looking at the examples you have now in this slide, uh, for example, the one of the four in the bottom row at the left, the one of the four planes. No? If after training a system for retrieving images from sketches, you want to retrieve images containing just planes in any position. With this example, you are learning to not to find planes, to find something that has the shape, but being four planes in the same orientation.
Right.
Uh, and so the system probably cannot generalize to I'm looking for planes in an airport.
Um,
The set is not allowing this creative search, as you also
right,
explained.
right, right, right. No, so this, I think the second comment was basically on the diversity of the planes, such as if are the planes only in certain orientation, and can it generalize to new orientations of plane? If I
Mhm.
understand correctly, right?
Yes, yes.
Yeah, which is exactly why. So we wanted to solve this problem right off the bat, and which is why we chose the photo data set as MS Coco. Now, MS Coco, given these photos, they have quite significant diversity of different objects in different backgrounds or different setups. And we've seen that this kind of MS Coco dataset does generalize and has this rich diversity. Of course, to certain limits, which is why later on we have with bigger datasets on which CLIP or other models are trained. But at least uh, to a certain degree, these are, because since the photo is diverse enough, we expect or we hope that these sketches would be diverse or equally diverse. It shouldn't be less generalizable, i.e., these kind of aeroplanes, if you, because the same aeroplane, there are 10,000 sketches, and the same aeroplane could occur maybe in 40 or 50 of the sketches, each in different background or orientations. And for a successful model to really learn, you have to really understand the underlying semantic, not just memorize the orientation of the plane or the airport, things like that. A memorization trick would not be sufficient for generalization, because this particular data set also has this. We purposefully keep a big, like a significant split between training and testing, which is like 7,000 on training and 3,000 on testing. It's pretty much what we do with the other data sets. We have equal number of training and equal number of testing. So we know really good how good the model is generalizing, and it's not an overfitting example. So we hope that, yeah, but because at the end of the day, we have just 10,000 sketches, which is compared to just image MS Coco, it's like goes to a million or 100,000, sorry, 100,000 or things like that, or some clip 400 million, things like that. Of course, it's not as diverse as that, but we hope that, okay, we need something which is more data efficient, like it works on few shot, which is why one of the approaches of it, while proposing FS Coco, we also extended one of the self-supervised learning for scene level sketches. One of the papers was basically comparing from raster sketch to vector sketch, such self-supervised tasks, so that it can understand the underlying ways of drawing. And we use that with the hierarchical decoder that we've mentioned, that how hierarchical decoder helps you in a self-supervised pre-training, such that you're even with these few quote unquote few sketches, you can still do a good generalization. So yeah.
Okay, thank you.
More questions from the audience?
Just one curiosity. At a certain point, you show some math, basically, that you use to define your loss function. Just out of curiosity, did you also try to prove some kind of convergence of the solution, maybe under some suitable hypothesis or something like that?
Yeah. So the convergence, the point of the, I think you're talking about this particular paper, this partialness, right?
Yes, when you revisit the loss function, yes.
Yes. So this is the loss function. So the convergence proof of it. The thing is that what we do with this, we cutely, like, we have the baseline FJSBR, and we know that, okay, that has a smooth convergence with triplet and L2 loss and things like that. All we really do is just make a weighted vector. Now we add a weight, but when you add this weighting function, this equation looks very similar to optimal transport. And we know the convergence proof for optimal transport problem or linear programming, they can converge in at most of 10 steps easily, or at least n log n. An optimal transport problem has a complexity of n log n, and that's exactly what we want from here. So we convert an existing equation, we add a weighting factor, and reform the equation into form of an optimal transport. Once you can reform it in optimal transport, now you have all these convergence proof, and you can know that you will get to a good solution pretty fast. So yeah, the optimal transport solution, the existing solution for optimal transport, one of these is the Dini classical implicit function that we use. That has it. They provide the guarantee of convergence in a complexity of O of n log n. So yeah, like could take an equation, convert it to a standard solution.
Okay, thank you. Just another curiosity, when you talk about captioning the sketch,
Right.
another super quick curiosity, did you also taking into account that maybe some caption could contain information about the color of the image, something like the man is sitting on the brown bench? I mean,
Yes, we.
Okay, you removed this part of the caption and something like that to make the comparison more fair, let's say.
No, so that's not that is something that we have not done, i.e. Like the image for the captioning, we want to match it like with the image captioning, because the objective here is that how good can you describe the scene. And the purpose was that the underlying intuition is that we know that, okay, humans can right, sorry, I'll come to this slide. Yeah, that machines, they can understand sketches or photos as machines can understand photos as good as sketches. And if we compare the photo with the caption where we have removed the color, i.e. we match the photo with the sketch captions, now the photo might describe some additional details. Say for example, here is a lighthouse. The photo might describe the lighthouse with the dry grass. Now dry is not a color information, but it's an adjective, which sketch has no meaning in it. So if you compare the photos with the sketch captions, then you would have a mismatch of information, which is why you cannot compare the captioning results with sketch captions. But what you can do, or what's the more principle that we want to see, is that sketches inherently lacks information, but the results, if the description of the sketches, because we match it, the predicted captions with the caption that is being written by a human. So if a human is describing something, your machine should describe the same thing. That's the principle. And if the machine describes perfectly what the human describes, you have a pretty high captioning, sketch captioning scores. And it's the same with photos, because if the machine that can understand, that can predict what a human is predicting given the photo, then you have a higher results in these metrics such as value one or cider, things like that. So if you do the mismatch of photo and sketch caption, then you would have a mismatch of evaluation. Because on one hand, you can think, okay, the sketch caption or the photos, maybe it's not describing the color information, but yeah, you want to match it to the what a human would describe and answer the question that can machines equally understand sketch as well as photos, because research shows that humans can. Yeah, that's the thing.
Okay, thank you.
Right.
Questions? Well, I have
Right.
some questions, Pinaki.
Yeah,
So,
sure.
and coming back to the thing with Jose pointed out about learning text prompts and like this kind of generation. So it's like, you know, the trend of DALI 2 and other things for photos, like learning text prompts and then generating these kind of pictures with like photos of corresponding to the caption that user inputs.
Mm.
I was thinking like uh, maybe it's like, what's your take on maybe generating something like these kind of creative sketches based on text prompts? Like, are we there in that direction? Like, how far are we from that direction? Or it's
Right.
like yeah.
So so to generate these kind of creative sketches from a text prompt, i.e., you want to see how creative are these machines or are they as creative as humans? To that, the first challenge definitely I think that comes to my mind is have a data set which is creative, something that we have seen with the creative sketch data set, that the data set is helps the model learn the creative process. But I would say that yeah, but simulating the creativity process or making the captioning process, what we have done up till now is create the captioning process a more stochastic, i.e., you see that these sketches, due to its ambiguity, they can have multiple interpretation. So it could be like the horse, as you can see the predicted captions. We have two captions for each sketch. These are predicted. We make it the network more stochastic. So it's not creative, but more of a different or variety of captions that is generated. But to understand the creativity of, maybe what are the multiple ways, or I'm not sure how you define creativity for scene level, and that definitely requires a proper prompt and a proper collection of data set on scene level. But yeah, we can do variety, but we probably cannot do creativity yet from text prompt when you're generating. And also, generating scene level sketches is also itself a big challenge because due to its complexity. Like we did try, we in the paper of FS Coco in the supplementary, we showed few results of how a network or a machine can generate scene level sketches given the photo as a prompt. And you would think that's an easy task, but due to these long strokes, because typically an object has just 10, 15 strokes. A sketch, scene level sketch can have easily like 50, 70 strokes. Like the complexity is very high. So even generating the sketch is itself a big task. And yeah, you would require there. I wouldn't say there isn't an approach, but so generation scene sketches is challenging. Second, what is creativity in scene level, and how do you get a data set which captures this creativity is the second challenge. And but what we have achieved up till now is just diverse captions for sketches. So
Yeah.
yeah. So I think yeah, we would need a data set, and it's probably another PhD. I think deserves another PhD to just explore creativity on scene level sketches.
Dali is also generating sketches.
It is.
I think so.
Mm,
Put
y-
sketches at the beginning.
Yeah, I think some examples.
Okay.
yeah. So with respect to DALI and all, so not just DALI, there has been quite a significant effort with differentiable rasterization. There is a CVPR 2022 paper also which tries to generate sketches. But the problem with those things, approaches, or I would more talk about DALI and the CVPR 2022 paper of differentiable rasterization, is that they more or less generate a photo, quote unquote, like you don't get this kind of vector information. So like it's not really simulating how a human draws, like drawing it in a sequential manner. rather than generating the entire photo at a time.
Yeah.
So this kind of saliency, what is more important, like we have seen that humans would draw the salient regions first, the less salient regions later on. So that process is also an important part of it. So yeah, so which is one of the issues with all these kind of differentiable rasterization for generating raster sketches, that they cannot simulate nicely the sequential nature of sketch drawing. Yeah, but DALI, yeah, in fact, I think, yeah, some approaches as big as DALI, or there is a lot of, like, Clip Forge is one of the important, famous paper that they are also trying a SIGGRAPH. I think it's accepted to SIGGRAPH this year. They use Clip network to this process of sketch generation.
Interesting.
In FS Coco, the sketches are recorded as images
No,
or as a sequence of so as strokes.
they are recorded as a sequence of strokes, yes, with the
Okay.
timestamps to it. And yeah, we basically just deploy a website, and so it makes it easier. You can use it on an iPad, you can use it on a drawing pad. So yeah, it helps scale quite easily.
Just another curious question. So it's regarding, like, because you were proposing object level like scene sketches. So I was thinking, like, these kind of object localizing objects, especially
Right.
in like these scene sketches, like how challenging is that kind of a task? Like the one that we do for MS Coco and coming to this kind of scene sketches, right?
Right. So localizing objects in a scene, I would say, so one of the things that we actually noticed when we were collecting this data set is that the previous data set, they were collected, as you mentioned, from object level. They would collect the objects together, create a scene out of it. But as you can see, just this two horse standing, the tree and the ground, they are more or less like, like connected in some sense. So humans, if you see the vector strokes, they don't really like one sketch on when you're drawing an object. Say you're drawing the tree, the same stroke follows towards the ground. It's a new or separate object again, a background object. So it's humans really don't hardly define these objects. Rather, they would continue from one object to the other object, and so that's an interesting part. So now if you ask a machine to segment out the objects, that theoretically could be done, but it wouldn't be an ideal approach because humans don't do it the way. And there are approach papers like for sketchy scene paper. Yeah, sketchy scene is a paper. They actually would understand a scene sketch by first localizing the each individual objects, and then they would do this kind of recognition or image retrieval, things like that. So there are approaches, but it's not a good direction. In my opinion, it's not a good direction to move forward because humans don't do that way. So
Yeah, makes sense. Well, any more questions from the audience? I'm more or less done from my part too. So
yeah, it's a nice to interact with you guys. Yeah.
yeah. Thanks a lot, Vinati. I mean, it's the direction that you have just put up. It's kind of really something really interesting to think on, and I think pretty sure we have a lot to explore. Like on these kind of directions. Especially, I think the FS Coco for sketch captioning, it might be one of the starting points for the next much more challenging tasks, and also for creativity, as we discussed on the sketch, like on conceptual sketch captioning can be one of the next tasks, like so.
Yes. Yes. Yeah.
Uh, yeah, so a lot to explore, but I wish you all the best for your PhD, and I know you you're doing great, and like all the best for the rest of the challenges, and looking forward to more of your works and like working on this direction. And
Thank you.
uh,
Thank you. Yeah.
and I don't know if Joseph would like to speak something more, add to it.
Okay, thank you for the presentation.
Sure. My pleasure.
Yeah.
So yeah, we hope this direction picks up momentum because it's critical for my survival.
Yes.
Thank you.
So,
Thank you, Pinaki. So,
thank you.
yeah. So, yeah, we have nothing to offer you much because it's a virtual presentation, but this virtual section, yeah. And
If you ever come to Barcelona, we will invite you for for lunch.
Sure, sure. Thank you. Yeah.
thank you so much. So thank you everyone and see you again and thanks again, Pinaki, for the wonderful presentation.
Absolutely. Yeah. Thank you. Thank you guys. Yeah, for inviting. And
Bye.
Bye.
bye bye.
Bye.